Hi everyone, my name is Karo Shaginyan. I'm from UCLA, and today I'll be talking about distributed logistic regression, building models without sharing data. And my mentors are Shorshan Jiang, Jihoon Kim, Lucila Ono Machado. So our motivation is that different institutions have the same type of data, yet there are restrictions on this data, and we can't share the raw data itself. Yet we want to, it would be a shame to just have this data and not take advantage of it. So we wish to ask, can we design methods that build models using these data in a privacy preserving manner? So what exactly, we should start out with the background and describe what logistic regression is. So logistic regression is a mathematical model in which independent variables, let's call them X, help classify a case into positive or negative dependent variable Y. It's best to understand this through an example. So we could go out and measure the temperature of a bunch of people. These people either have a fever or they don't. And we could take all that data and stick it in a graph like you see on this slide. And so on this graph, the y equals 1 axis corresponds to a fever, and the y equals 0 axis corresponds to no fever. So you'll notice the points on the top right of the graph, and these are the points that correspond to the people who've had fevers. And if you follow those points down to the x-axis, those are the recorded temperatures for those people. Similarly, for the points on the bottom left part of the graph, those are the points corresponding to people who don't have fevers, and the x-axis tells you the temperature that was recorded for those people. So what logistic regression does is it tries to draw out this S-shaped curve that you see on this graph. And once we have this curve, we can ask questions like, if I have a certain fever, if I have a certain temperature, what's my probability of having a fever? So throughout the talk, when I say we need to fit a model to the data, what I mean is, how do we draw out that S-shaped curve? And that's what logistic regression is. And algorithmically, the way we do this is we use an iterative process. We use the principle of maximum likelihood, which says we will draw out the curve that makes the data points that we've collected most probable. So traditionally, logistic regression has been performed on centralized data sets. So following our previous example, someone will go out and collect temperatures, and they will stick this into a file or a single database, and typically one institution will have access to all this. What we want to speak about now is horizontal partitioning of the data. So as you see on the table on the slide, we have multiple institutions, and they all have the same type of data, but they don't have all of it. They just have parts of it. And we still want to be able to fit a model to the data while acknowledging that these different institutions can't just copy this raw data and pass it around to people. So again, the question we wish to ask is, can logistic regression be done in a distributed manner? And the answer to that is yes, it can, using the grid binary logistic regression, or GLOR. The GLOR model integrates decomposable partial elements or non-privacy sensitive prediction values to fit a model to the data and obtain the variance-covariance matrix. Experiments show that GLOR's results are practically the same as traditional logistic regression, yet it is computationally faster. So let's see how this works. So here's the pipeline for GLOR, and the way it will work is we will designate a central server, this right here, and these institutions, so I will refer to this as the server, and these institutions as the clients. So what these clients will do is that they have parts of their data, and they'll perform some function on their data. And so let me back up for a second. Remember that the way we fit a model to the data is we run an iterative process. So let's say we're starting off in the first part of the iteration. So in the first iteration, these institutions, these clients will run some function on their data, and they will send the results of that function over to the central server. We'll send it over to the central server. And the central server will take these intermediate results and combine them and send the results back over to the clients. And in this way, what we see here is that, and so that's the first iteration. This will sort of continue. These institutions will take the data that they receive from the server, apply a function to their data with the input from the server, and send those results back to the central server, and the iterations will continue until we fit a model to the data. And so what we're seeing here is that even though these clients have their part of the data, they're not sending the raw data. They're sending a function of the data which is not privacy sensitive to the server. So in this way, we're able to fit a model to the data. So what I worked on this summer was the implementation of this method, and my mentors had implemented this code in R, and what R is a programming environment for statistical computing, and it was very problematic. One of the issues was that it used busy waiting, and what busy waiting is, for those who don't know, is when there's some computation waiting on other parts of the computation, the computation basically is stuck in a loop, and it's continually polling, draining CPU resources, and asking, hey, is what I'm waiting for ready? Hey, is what I'm waiting for ready? So this is very inefficient. The other problem with this code was that the clients had to wait for each other. The reason for this is because the server was not asynchronous. And so aside from the clients being in lockstep for the iterations, they really should be independent, so this was a problem. It's also hard to take this code and to put it into a real-world environment. We can't just take this code and make a web application out of it for people to start using, or we can't change the underlying protocols very easily. So to address these issues, we implemented this in Java, and to handle the busy waiting problem, we used semaphores. And what semaphores are, for those who don't know, is it's an intelligent way for computation to wait on other parts of the computation. So if I were a thread, if I were some computation and I needed to wait on something, I would ask the runtime system, hey, put me to sleep and wake me up whenever what I'm waiting for is ready. We also made the server multi-threaded, so that in this way we were able to handle the clients asynchronously. It's also easy to take this Java code and to integrate into a real-world environment. We could take this Java code, we could make a Java applet out of it, or we can change the underlying protocols very easily. And from what I understand, that is something that iDash is working on right now to change the networking protocols and to make it more secure. So I just want to run through a flow of the client-server interaction for you guys to get a feel of what is going on. So we'll start out with the clients and the server. And what the server will do is it'll spawn off a computation thread. And then at this point, the clients will begin initiating a connection with the server. So client 1 will connect to the server, and for each client that connects, the server will spawn off a new thread. So right now we have a thread for client 1, and client 2 and 3 will connect to the server, and they will each get their own threads. And at this point, the server has n+1 threads, where n is the number of clients, and it also has a computation thread. They're waiting for it to perform its task. So at this point, the clients will perform some computation on their parts of the data, send that over to the server. The client threads will take this data and stick it into shared memory for the computation thread to get to work on it. So the computation thread will perform its computation on the data. So what's happening here is that the server is combining the intermediate result for this first iteration, and then the client threads will send that over to the clients. And so this was the end of the first iteration, and this will sort of continue. And that will until we fit a model to the data. So to summarize, what we were able to do with Glur is we were able to perform logistic regression without sharing the raw data. And we were able to do this by designating a server that handles the intermediate results and allows the logistic regression algorithm to progress. So in the future, it'll be interesting to see how these techniques can be applied to other sorts of models. And that'll. Oh, and for my acknowledgements, I'd again like to acknowledge my mentors, Nate Heinzman, CalIT2, iDash, DBMI, and NIH. At this point, I could take any questions if there are any.